All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's just jump into it. Okay, there we go. So last time we went through some probability teasers. Jhevon had a lot of fun telling you guys you were wrong. It's time now, though, that he makes up for that and starts telling you guys how to get the problems right. So that's what we are going to be talking about. I do want to go over a couple of the problems that we saw last time, just to make sure that we kind of see why that happens, why that was the answer, and maybe show off a couple techniques that I will teach you guys more in depth as we move forward. And the second one, we did some of it. I'll probably just really quickly go over that again, but it's going to be a nice segue into the next topic I'm going to want to do. Let me make sure I have my notes here. So we're going to do that. Let's talk about the Monty Hall problem. Okay, so just to remind you, this is the problem where you're on a game show. There are 3 doors, and you're asked to pick a door. Behind one door is a big main prize, like a car. Behind the other doors are goats. And you pick a door. The host, though, opens one of the other doors that you didn't pick, shows you a goat, tries to get into your head, psych you out. And he's like, hey, you want to switch your answer? And the question is, should you switch your answer? And as a matter of probability, the answer was, yes, you should switch, right? Yes, you should switch. Now let's talk about the why. Now there are a couple ways that you can see this. And one, we can draw a diagram. Which is it's going to be a technique we will learn about later. There are going to be various kinds of diagrams that can be very useful in a probability setting. But sometimes it's just really easier or nicer to just, you know what, I really don't know. Let me just draw a picture, kind of see what would happen. So here's a diagram about 3 situations. And here is the car. Let's pretend the car is behind door number 3. Of course, we don't know that, right? So pretend the car is behind door number 3. You can make 3 possible choices, right? So the car is really behind door number 3. Monty doesn't tell you this, of course. He says, pick a door. And you're like, I choose door number 1, Monty. So here is the door you pick, right? So this door you picked. This door Monty opens. Before asking you to switch. Okay, so in one universe, right, in one timeline, you pick door number 1. What's going to happen in that case is because Monty knows that the car is behind door number 3, he is going to open door number 2, and he's going to show you, hey, there's a goat here. Do you want to switch? And what would happen if you switched? You would actually win the car, right? So if you switch versus stay, right? In the first scenario, if you actually switch, you would win the car. Someone came in and like scared me just now. If you switch, you actually win. If you don't, you would actually lose, right? So that's one timeline, right? But maybe in an alternate universe, there's a different version of you who didn't pick door number 1. You could have said door number 2. Right? So time rewinds. Monty says, pick a door. You're like, door number 2, right? Now, remember, the car is behind door number 3. We don't know. What would Monty do? He would open this door, and he would ask, do you want to switch? And what would happen if you switched? Well, you originally picked door number 2, and the car is behind door number 3. So you would win if you switched. You would lose if you stayed, right? Now, let's say in some universe, you pick door number 3. Now, Monty can open either one of the other doors. Let's say he just opens this door. Shows you a goat, asks you, do you want to switch? You'll say, what would happen if you switch then, right? Because you're on the car now. So if you switch, you're going to go off the car. So in this universe, you actually lost, right? You would have won if you stayed. However, what do you notice about the switch column? Two out of 3 times you would win. Right? Notice that in the stay column, only 1 out of 3 times would you actually win, right? You would lose in both of the first scenarios. And a similar outcome would happen if the car were behind doors 1 or 2, right? The same sort of thing would happen, exactly, right? You'll realize that proportion-wise, 2 out of 3 times you would win by switching, right? So it's not just, oh, is this guy trying to psych me out? Or, you know, there's a meaning behind door number 1, like the number 1 is special, you know, 1 is the loneliest number, that's got to count for something, right? Like it has nothing to do with any of that. Like mathematically, you draw out the diagram, you count all the possibilities, and it's like 2 out of 3 times. If I switch, I win, right? Should you switch? Yeah, I should switch. There's another way that, and I don't remember if this was the solution that was given, but there's another way to actually look at it. And this is, it's actually a kind of a weird technique as math goes, but sometimes it works. Increase the difficulty. Now, very commonly in mathematics, when you want to solve a difficult problem, what you do is you kind of simplify, right? If you have a problem with 10,000 moving parts, you just imagine that the problem had 2 moving parts or 3 moving parts. And when you figure it out on that level, you then can extrapolate your results to the 10,000 moving parts. Here, we're going to do quite the opposite. We're going to increase the difficulty. Now, for some people, it just now makes it obvious that you should switch. What if we had 1,000 doors? Now, bear with me. At first, you might say like, wow, that's like worse than we had now, but it's going to be obvious what the answer is once I I tell you, what if we had 1,000 doors, right? So you have door, 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 dot, 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 door, 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 dot, 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 door, door, dot, dot, dot. You have a bunch of doors, door, 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 dot, 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 door, door. Ultimately, now you have 1,000 doors. Okay. Now the car is behind one of them. So Monty says, here's the door you picked, right? You pick this. Here's what you really need to recognize. And once you recognize this and you kind of keep that in your mind, you're going to realize why it makes sense to switch right away. What are the chances that you're right? Not great, right? Like, chances are you didn't pick the car. Let's be real, right? You're not that lucky, right? You have 1,000 options. The chances that you are right is 1 in 1,000. There's a 999 out of 1,000 chance that the car is in one of the other doors, right? Well, it's like 1 in 1,000. There's 999 over 1,000 chance it is in another door. Now, Monty opens the other doors. So Monty's like, oh, you picked door number 1? Well, looky here. Goat, 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 goat. He's really putting it on you right now. Like, you're just seeing goats all over the place. You're like, holy man, right? Really, goat, 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 goat. Now there's one other door. And Monty asks you, do you want to switch? Hell yeah, I want to switch. Like, chances are the car is behind a door that I did not pick. Now you're giving me the option that the only other closed door is the door that I didn't pick. Right? There was a 1 in 1,000 chance I was right in the first place. I knew going into this that there was a 999 out of 1,000 chance that it would be in another door. And now you're offering me the other door where literally none of the other doors are an option anymore. Hell yeah, I want to switch. There's a 999 out of 1,000 chance that it's in the other door because that's not going to change. I knew that from the very beginning. I had a 1 in 1,000 chance that it was door number 1. So yeah, chances are I was wrong, which means given the opportunity to switch, chances are I would switch to the right one, right? So chances are you were wrong in the beginning. So chances are you'd be right to switch. Why can I not spell switch today? Right to switch to the only other available door. Right? Right? And a lot of people find the answer way more obvious in that case. It's like, or so you could say like 1,000,000 doors. There's a 1 in 1,000,000 chance that you pick the right one in the first place. Chances are it's somewhere else. Now he eliminated all possibilities except one. It's still true that chances are it's somewhere else. And now you have that somewhere else handed to you on a platter. Of course you should switch. Definitely you should switch. Now, will you always win if you switch? No, but you definitely increase your chances. And that it was the same thing with the 3 doors. It's still true that with 3 doors, when you pick one, chances are you're wrong. There's a 2/3 chance you are wrong, right? There's the majority of the chance you're actually wrong. The thing is, when it's this small, people don't really notice that. And when one door is eliminated, now they're like, oh, it's a 1 in 2 chance. Maybe he's trying to psych me out, or maybe it doesn't even matter. I mean, it's 50-50 at this point, right? And no, it matters. It definitely matters. And if you use 1,000 doors, you will see that it matters. Because what are the chances you were right in the first place? Not great. You should definitely switch if given the opportunity. So yeah, that was the solution to the Monty Hall problem, and shows one sort of technique that is very useful, and that's just like drawing a picture. There are other pictures that we call like tree diagrams. You can draw tables, you can draw other things, and we'll talk about those diagrams moving forward. But drawing a picture often helps, and you can like see, oh yeah, switching is better. Now, here's another way. Sometimes you can't actually draw a picture. Like, what are you going to do? Draw 2 kids running around in a yard? Like, you can't, right? What is the picture that will help with this problem, the 2 girls problem, right? What would help here is for you to start to think about a way to consider all possibilities, right? And you want to think of a convenient way to do that. And we spoke last time about how thinking of the children of these people as a set of children is not quite efficient, because, you know, a set doesn't care about order. A set will eliminate information if it repeats. And so it has some issues with thinking about it as a set specifically. There are other cases where you where you want to think of it as a set, but not here really, because you probably want to know how to conceptualize the older child versus the younger child. Some order has to happen, right? And so you wouldn't think about sets. So you would consider all possibilities to be sets of this type, right? Like x comma y, such that x is boy or girl, or y is and y is boy or girl, right? So these are the total options, right? And that's for like part A, where we're giving no restriction, right? So now when you look at that, you're going to notice that, well, you can have a boy and a boy, you could have a boy and a girl, you could have a girl and a boy, you could have a girl and a girl, right? And so now you look at the size of the total options, well, that's 4. And you look at A is the event we want, which is 2 girls. Now an event, we normally think of this as like an occurrence or something that happens, but in probability, an event is just another set. An event is going to be a subset, to start using the language that we've been developing, is a subset of the set of total options. The set of total options, by the way, is called a sample space. I'll define that later on. But the event we want is the event of having 2 girls. So now the thing is, the size of the event is 1, and therefore the probability of 2 girls is 1/4, right? So that's why in answer A it was 1/4. For B, the total options changed. You know 1 was a girl, right? Which means the possibility of both boys isn't an option anymore. So while in general you'd have boy, 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 girl, girl, boy, girl, girl, Now, this, not an option anymore. So this means the size of the total possibilities was 3. And again, we want A to be the 2-girl scenario. The size of A is still 1, which means the probability of 2 girls in this case is 1 out of 3. We moved on to C. We were told the older child, and that was the key phrase, the older child is a girl, which means now our total options, well, before we could have a boy and a boy, we could have a boy and a girl, we can have a girl and a boy, we can have a girl and a girl. But now, no longer an option because older is not a girl. Right? We also do not have this. Older is not a girl. Should probably conceptualize this a little bit more specifically, where we're saying X is the older child and Y is the younger. Right? Now, of the 4 total possibilities that we had when we were thinking without restriction, 2 of them aren't valid anymore. So we're now in the case where the total options, the size of the total options is just 2. And we want A equals 2 girls. So the size of what we want is 1. And so now the probability of 2 girls, if older is a girl, well, that's just 1 out of 2. And I think we went over those last time, so I just quickly went over those again. Now, the solution to the last part is going to segue nicely into what I actually want to talk about today. So I'm going to actually talk about the solution there. See, this one is a bit tricky, so you have to be careful. Because of possible overlaps. And you'll see what I'm talking about soon. Now, we also want to keep track of the day born, day of birth, right? So in part D, you know one was born on a Monday, right? So now the day of the week is now an important factor for you, right? So now what we can do is we can set the total options, which again is called a sample space, which we'll call the set S, but I didn't introduce this notation yet, so I'm kind of writing things out like I don't know what I'm talking about. But it would be something like it'd be something like W, X, Y, Z, such that W equals boy or girl, and we can think of that as the older. X is the day for older. Y is a boy or a girl, younger. And Z is the day for the younger. Right? Now, why do we have to have days for both of them? Is because we were not told which of the children were born on a certain day, right? We weren't told that the older girl was born on a certain day or the younger girl was born on a certain day. We just said one of the children were born on a certain day. So this child could be the first child or the second child. We don't know. So we have to make provisions for that option. Whether or not it's the first or the second child, we want to keep track of the days, right? So now you start to look for, so what do we know? One child is a girl born on Monday. So this means we have two cases. So case one is the older is a girl born on Monday. Or case two, the younger is a girl born on Monday. So what would the coordinates look like here? The older is a girl born on Monday, which means I know that the first position is a G and the second position is an M for Monday. The thing is, I don't know what the third and the fourth position are. Now, the third position could be a boy or a girl, and the fourth position could be Sunday or Monday or Tuesday or Wednesday or Thursday or Friday or Saturday, right? There could be 7 options there. Over here, the thing is I don't know about the older child, but if I assume that the younger is a girl born on a Monday, I have very similar options. I would have, it could be boy or girl in this position, and it could be Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Okay. Now, this is something I'm going to talk about pretty soon, right? But at the moment, you can just take my word for it, even though later you're sort of going to take my word for it anyway. So what you notice here, there are 7 options. And here, there are 2 options. It turns out that we have something called the multiplication rule that's going to tell us if we are constructing an experiment where we have a certain number of options in each case that we can pick, then the total number of options is going to be the multiplication of the number of options of each stage. So here, you would say that there are 14 total options. Similarly here, there are 2 options and 7 options for 14 total options. But careful. Both options include one particular guy. GM, right? You'll notice that I can pick that for both options. So I'm kind of double counting there. So of the 28 total options that I have now, because I have 14 in case 1 and 14 in case 2. However, one of these guys is an overlap. There's going to be a guy that's in both case 1 and case 2, and I'm going to ignore him for one of the cases. Out of the 28 total above, we ignore the overlapping case. So now I finally get to the fact that the size of my total is going to be 27. So now I know that's going to be the denominator. Okay, now what do we want? So in case 1, here's what we would want. We would want, this is G, this is M. In case 1, I would want this to be G, because I want to know that there are 2 girls, which means this option is now chosen, that it's definitely a G. I want it to be a G, which means the only things that I can pick is the days: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? So now I have 7 options. And in case 2, boom, boom, GM, I definitely know that I want a G here because I want to know that there are 2 girls, which means over here, I can have Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, or Saturday. But in fact, again, because of the overlap, I'm going to ignore the Monday because that would just overlap with the previous case. Ignore Monday. And so what you have here is 6 options. That gives you a total of 13 options for what we want.
I'm sorry, could you repeat why you're not going to include Monday for the second case?
Because it would be the same thing. If I put Monday here, I would get GM, GM. And over here, I also have a GM, GM. I'd be double counting a case, right?
Okay, thank you.
If I include Monday, I would get a GM, GM in both cases. It's really one situation, but I would be counting it twice. So I don't want to count it twice. So I ignored it here. So ultimately, I have 13 total options. So this means the size of A is 13. And so this means, in this case, the probability of 2 girls is the number of ways we can get what we want divided by the total number of possibilities, 13 over 27. Which last time probably seemed like a very random number to you, but of course it wasn't random at all, was it? Like it comes down to you figuring out how you're going to dissect things, how you're going to think about the problem, and then just kind of counting, right? Now this problem admittedly is a very difficult problem. It's not something that I expect you to just know how to do right off the bat. But eventually, after a couple weeks of me like teaching you from the basics going all up, yeah, eventually I'd expect you to be able to work your way through a problem like this. But of course, there's a learning curve, so don't worry about if you're like, I don't think I would have been able to figure that out. You're going to be able to figure this out soon because I'm going to give you, advice on when to do what, when would you want to draw a diagram, when would you want to look at things as coordinates, when would you want to look at things as sets, and how to actually figure these out, right? Which is actually super important. Because now now that I remember, on test 1, there were times when I gave you guys all the formulas for finance. And so all you had to do is just know when to use which formula. When do I use sinking fund? When do I use amortization? When do I use the PE to the RT, right? You just had to know when to use it because the formula was there. And a lot of people were picking the wrong formulas because you never paid attention to when you were supposed to use it. When in class, I literally took like 10 minutes of the lecture and explain to you, use these in one-time payment situations, use the sinking fund when you're saving up to something, use amortization when you're paying down debt. Like I specifically told you when which formula applies. Like that information is important. It's not just important to know the formulas, it's actually important to know when to use the formulas, when to use what strategies. So as we move on, I'm going to start to give you advice like this. Here's when you might want to do something like this. And then this problem that at this point the solution may not seem very obvious to most of you, and most of you might feel like I would have never been able to figure that out. You will eventually. You'll know that this is kind of what you'd want to have done. you know you won't want to use sets, you'd want to use coordinates, then you're going to know how to count which coordinates you want, and so on. So, yeah. So, in the end, we see counting is important, right? Why is counting important? Notice that in these problems, and in probability theoretically, you're always looking at a set of things. There's a set that represents all total possibilities, and there's another set that represents the possibilities you care about, right? Now, at the end of the day, what you need to be able to do is you need to be able to count how many things are in the total possibilities. And you also need to be able to count how many things are in the possibility that you care about. At the end of the day, you need to know how to count. Now here, we didn't have to count that high. There are only 4 things. This will not always be the case. Sometimes there will be many, many, many things. And you don't want to have to write everything out to kind of know how many things would be in a certain set. You will notice here that I did not write down all possibilities here. I didn't take my time to write down all coordinates, GM, GS, GM, GT, GM. Like, I didn't waste time doing that. I just know there are 14 things here, right? And I knew that because of a counting strategy that I have. I just know that when I'm counting things of this type, I would just multiply the number of options in each case. I just know that that's how I would count. So I'm counting without actually counting. I'm counting via some shortcut, right? Now that skill is counting efficiently is a skill. This is called the area of math that deals with this, like learning how to count, right? Like everyone thinks they know how to count because you're like, I know how to count to 10 since I was like 3 years old. Okay, I know how to count. Like, yeah, you think you know how to count. Most people think they know how to count. The area of math that teaches you how to count is called combinatorics, which is basically the study of counting without actually counting. And the thing is, when most people think counting, they think of 1, 2, 3, 4. This is what's technically known as enumeration. What most people think counting is. No, 1, 2, 3, Mississippi. Right. That in technical terms is called enumeration, right? We want to count without having to enumerate stuff. And so that the study of how to do that is called combinatorics. And it can get quite crazy because the world is complicated. You know, we have supercomputers, 256-bit encryption. How many guesses would someone have to guess a password? If it has, 13 characters, 13 positions, and in each of those positions you can have 27 characters or whatever. Like, you don't want to list all possible passwords to kind of know what the chances of cracking your code is, right? You want to be able to count. You want to know what the probability of someone breaking your password is, right? And that requires efficient counting. If we didn't have the efficient counting, we'd still be counting like, yeah, I mean, you know how long it would take for you to count to 1 billion if you count one number every second? Does anyone know?
1 year.
What?
1 year.
1 year. Great. Okay. I can tell you what the answer is for 1 million, and maybe that will help you. You can count to 1 million in 11 days if you count one number every second. How long would it take you to count to 1 billion, going like 1, 2, 3, blah, blah? 32 years. If all of you started counting since you were born, you would not have reached 1 billion yet, right? So this is kind of telling you the importance of what I'm trying to say. There are times when you want to be able to count into the billions. You ain't got 32 years to come up with the answer to that test. You got an hour, right? So yeah, knowing how to count is going to be very important. So this leads to, I think I want to do them both at once, section 7.3 and 7.4. This is basic counting principles / permutations and combinations. Seven 7.4 is where you deal with permutations and combinations, but the way I like to introduce this, it's just kind of naturally flow into that section, so I don't really want to dissect them as two sections. Just going to do both of them. The first thing I want you to know about basic counting is the thing that I mentioned earlier. There's something called the multiplication rule. Here is what it says. Suppose A, B are finite sets. Then the number of possible two tuples, that is things that look like a coordinate A, B, where A comes from the set A and B comes from the set B, is the number of possible two tuples that can be formed is the size of A times the size of B. This can be generalized. So suppose A1, A2, AN are finite sets. The number of possible n tuples. So these are things that look like A1, A2, A3, ... all the way down to AN, where the AI are in the AI. So A1 is in the big set A1, A2 is in the big set A2, etc. That can be formed is the size of A1 times the size of A2 times the size of A3, multiplying all these together times the size of AN. I'm going to tell you three different versions of this because some might be more important than the others. Like the way I stated this just now would help you figure out the girl problem. In part A, B, and C, you would just know, oh, I have two options, boy, girl for the first position, two options, boy, girl for the second position. So there are 2 times 2, 4 total options, right? Now, I didn't have to write them all out to see that. I could just know that there were 4. Similarly here, if there were 4 coordinates and I know there are 2 options here, 7 options there, 2 options here, 7 options there, then the total possibilities would be 2 times 7 times 2 times 7, right? Which is a lot. I wouldn't want to have to list those all out. However, if you told me that, oh, I know there's a G here and I know there's an M here, so now I only have to figure out how many to fill in the others, it's just the 2 times the 7. I know it's going to be 14 by this rule. This can also be stated as, there's another way you might want to look at it. If an experiment has m stages, you can think of setting up a coordinate as with n things in it as something with n stages. You're doing the first coordinate, then the second coordinate, then the third coordinate. These are all stages. As m stages, and you know that n1 is the number of possible outcomes for stage 1. N2 is number of possible outcomes for stage 2, ... and so on. Nm is the number of possible outcomes for stage m. Then the total number of possible experiments is n1 times n2 times n3 times n sub m. Yeah, so that's called the multiplication rule. Let me do one quick example and then I'll let you go and we'll learn to count more efficiently some other time. Example. A is the set 1, 2. B is the set little a, little b, little c. How many possible xy can be formed if your x comes from the set A and your y comes from the set B, right? That's the question. Well, by the multiplication rule, since the size of A is 2 and the size of B is 3, there are 2 times 3 total 2 tuples, right? So I can know that there are 6. There's definitely 6. 2, just to show you by enumeration, you could go, well, that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. And I could count them one at a time, 6 total possibilities. Now I'm showing you this because there are times when you don't want to have to worry about being sophisticated. You just want to get the problem done, and you should just enumerate, just list all possibilities. Sometimes it's not going to be that many, and it's just safer to just list them. Like with the 2 girls problem above, like I wouldn't worry about trying to use some sophisticated counting rule. I mean, it's going to be clear that I only need to worry about 4 things if I just start listing them. There are not that many options. I would just list them. But there are times when you don't want to have to do that. But there are times when you do. So I do want you to know both ways. I don't want you to throw away the counting that you know about before. But there are better ways out there that I want you to be aware of. So we are going to stop there for now. We will pick up with more on counting next time. We'll spend... it's possible that we spend all of next week on counting and then move to probability the following week. But it's also possible that I might finish counting on Wednesday and then we start probability on Friday. Because I have a bunch of examples I want us to go through together, and it just depends on, I guess, how fast you guys catch on. So yeah, we will stop there for now. Thank you for your time and attention. I have another class right after you guys, so I'm going to let you guys go. I will see you in the next one. Ciao.